Yeah, we'll find out. Okay, so last time we introduced the concept of intersymbol interference and trying to find a pulse that fit within our allocated bandwidth that met this intersymbol interference criteria. There's some problems with, we found that the optimal pulse to actually limit intersymbol interference is the sync pulse. Okay. Sync pulse is optimal for low intersymbol interference, ideally 0 in the smallest available bandwidth. Okay. But there are some problems with the sync pulses. They can't be realized. Okay, and we can approximate them. But they also have some other issues that they roll off relatively slowly. That means that if there is a little bit of timing error, then it is the intersymbol interference can go up drastically. But we found for these, they have a spectrum is rect of f over 2b0, where b0 is 1 over 2 times the pulse width. And the bandwidth is b0. Again, it's a little strange because 2b0 is that width, but b0 or our bandwidth is just the positive frequencies. So this is the spectrum actually of our sync pulse. Okay. So I think I had that on a picture. So this is, again, this is a little odd at first glance because normally we talk about pulses in the time domain leading to syncs in the frequency domain, but this is a sync pulse in the time domain having a pulse. It's not really a pulse, it's a rectangularly shaped spectrum in the frequency domain. So, but again, there's some issues with the sync pulse. So is there a good approximation or perhaps a better pulse to use, a compromise pulse? And there is, it's called the raised cosine pulse. And it has the advantage of, it has a smoother transition band. The transition band is this sharp edge. It's not a sharp edge in the frequency domain. It has a smoother transition band. The implication of that in the time domain is that it has actually faster roll-off, which means smaller intersymbol interference when timing errors are present. It has zero intersymbol interference with no timing errors. But the disadvantage it has over the sync pulse is it has a wider bandwidth. Than the sync pulse. Or if you're limited in bandwidth, that means if you used raised cosine pulses, you'd have to transmit at a slower rate than you could using sync pulses. But again, sync pulses are unrealizable anyway. Okay. So I'll write down the expression for a raised cosine pulse. It's a little bit long. It's actually a sync, but multiplied then by another term, cosine 2 pi alpha b0 t. Alpha is a parameter that you can vary to get the behavior you want. 16 alpha squared b0 squared t squared. So this is a raised cosine pulse in the time domain. Do I have a, yeah. This is actually showing different spectra, and this is what the raised cosine pulse looks like in the time domain. Actually, as you vary alpha between 0 and 1, and that's a restriction here, 0 is less than alpha less than 1. For alpha equal to 0, this term is 1, and the raised cosine pulse becomes the sync pulse. Okay. So the alpha equals 0 pulse here is a true sync pulse. At the other limit, alpha is equal to 1. You'll notice the much lower side lobes that are present with the alpha equal 1 than the alpha equal to 0. So it actually goes to 0 more rapidly than the sync pulse. You know, again, ideally, it's infinite in duration, but we can come up with a finite duration approximation to it that is more like the theoretical pulse than we can with the sync pulse because of the high side lobes. So this looks nasty. Well, it is kind of nasty, but it actually has a fairly nice Fourier transform or spectrum. It is a constant out to a frequency F1, and I'll give you the formula for F1 in just a minute. And then it has this form out between in another range of frequencies, 1 plus cosine pi absolute value of f minus f1 over 2b0 minus f1. This is for frequencies between f1 and 2b0 minus f1. And then finally, it's 0 outside of that. So let me back up. I don't know why I had these in this order. This is the spectrum of the raised cosine pulse, again, as a function of this thing, of this parameter alpha. With alpha, it's the sync pulse. At the other end, with alpha equal to 1, you know, it has this smoother shape in the frequency domain. It still is a finite bandwidth pulse, though. It has finite spectrum. You notice with alpha equal 1, though, the bandwidth is twice the alpha equals 0, but it still is finite bandwidth. Okay. And that's important to us because we can fit it into any sort of transmission channel that actually has finite bandwidth. Okay. So where B0 here, I wrote it over there, but I'll write it again, is 1 over 2 TB. So TB is our bit interval. And roll off factor alpha is related to F1 by, I'll write it up here, alpha is equal to 1 minus F1 over B0 for 0 less than alpha less than 1. So the idea here is, based on the desired bandwidth that you need to fit your pulse into, you can find the corresponding value of alpha. Okay. So the pulse bandwidth would actually be given by this last non-zero term. So this frequency as a function of alpha is actually 2B0 minus F1. We can solve for F1 from this equation, and then get the transmission bandwidth is 2B0 minus F1. So B0 is the is the bandwidth of my sync pulse, and then my raised cosine pulses have wider bandwidth than my sync pulse. Or, and here's our design formula. The transmission bandwidth is B0 times 1 plus alpha. And so that's what I would use to actually find my alpha value, is this equation. So we'll work through an example here. But as alpha varies between 0 and 1, the required transmission bandwidth varies between B0 and 2B0. Okay. As alpha increases, I get faster roll-off in the time domain, which leads to less intersymbol interference. So I want to try and use the largest alpha value that I can. Okay. So let's look at an example, I think, similar to one of the homework examples. A channel has a bandwidth of 20 kilohertz. We want to transmit data at a binary rate of 30 kilobits per second. What alpha should be used? Okay. So TB is 1 over RB. And then this B0 parameter that's in these equations is actually 1 over 2 TB, okay, or RB over 2. Okay. So in this case, that would be 15 kilohertz. But from our transmission bandwidth formula, it is B0 times 1 plus alpha, or RB over 2 times 1 plus alpha, or 15K times 1 plus alpha. So solving for this formula, 20K is 15K times 1 plus alpha, leads to alpha is equal to 1/3. Okay. So that's the value of alpha that is necessary for a raised cosine pulse to fit into the given bandwidth. Okay. Now, smaller values of alpha would work, would actually take up less bandwidth, but you want to use the largest value of alpha you can to reduce the amount of intersymbol interference. For a sync pulse, an alpha 0, a bandwidth of only 15 kilohertz is actually necessary, half the bit rate. Okay. This is actually going to use up the full 20 kilohertz. So, but using raised cosine pulses, the binary rate must satisfy the binary, the bandwidth is this is for alpha equals 0. This is for alpha equal to 1. So with the alpha equal to 0, the bandwidth is actually, at the minimum case would be, or RB has to be between those two limits on the bandwidth. The excess bandwidth is the greater bandwidth required by the cosine pulse over the sync pulse bandwidth. So the excess bandwidth Fx would be Bt minus B0, which is just alpha times B0. Okay. And that's the bandwidth above the Nyquist channel. Okay. So let's talk about one other example. So we've talked about a T1 system before. This is kind of a standard that's used in the telecommunications with networking industry. For a T1 line, the binary rate is actually 1.544 megabits per second. Or the corresponding bit rate would, bit duration would be the reciprocal of that, or 1 over 1.544 megabits per second. This used to be considered high-speed internet. By the way, you'd have a T1 line maybe feeding an entire university. I remember at one time, UE had a T1 line supplying internet to the entire university, all classroom buildings as well as all dorms. Now no one's happy unless they have like 100 megabits per second, right? Per household, for your streaming video, and anything slower than that is unacceptable. So, but it's not really true. I think most people, you can stream acceptable video, usually, at just certainly on a T1 line, but no one likes to wait 5 seconds for their file to download when you can wait half a second for your file to download, right? So, and then now with 5G cellular networks, we can download our entire 2-hour movie in 10 seconds or something, right? So, but this used to be considered high-speed internet. They still talk about T1 lines, but now they'll often talk about 20 T1, the equivalent of 20 T1 lines or something. So it's still used. So the required bandwidth is RB over 2, or 772 kilohertz. This would be with alpha equal to 0 or using sync pulses up to RB, or 1.544 megahertz, using cosine pulses with alpha equal to 1. Okay. So, and this is often, given no other information, we'll often, and we've used this up to this point in the semester, we'll often talk about the required bandwidth for a binary channel being equal to the binary rate. Okay, and that's a pretty good approximation. Okay. Again, with sync pulses, you can actually get by with a smaller bandwidth. Okay. Again, this is baseband as well. When we modulate, it doubles the required bandwidth for the band, because then you've got the negative and positive frequencies, unless you use some sort of single sideband modulation property. Okay. The other thing that you'll hear about in communications, so how do you generate these pulses? Typically, it's done with pulse shaping filters. If you go back to the last lecture, and we had a complete transmission system, we had a pulse shaping filter at the transmitter, which we called G of F, and then we had the channel frequency response, H of F, and then we had another filter at a receiver. All three of these give us the spectrum of the final processed pulse. What we would like is this thing to have this raised cosine pulse spectrum. So it has, because this is what we're actually sampling. So to have this minimal intersymbol interference, we want P of F to have that raised cosine spectrum. Okay. So how do you get that? Well, one way is you let G of F, H of F to be 1/2 of your desired square root of your raised cosine pulse spectrum. Now, in order to do this, you have to know what the spectrum of the channel is, which means that you have to take some sort of frequency measurements, test your channel to measure the frequency response of your channel, and then design your G of F filter so that the product of these two has, I wrote down the spectrum cosine pulse, that this is equal to the square root of that, and then Q of F is also equal to the square root of that, so that the product of these is equal to P of F, and you get your raised cosine pulse spectra. But then Q of F here then would be said to have a root raised cosine frequency response. Okay, and that's okay. I think that's all I'm going to do today. I'll let you go a little early. I don't have your exams graded. I will try to get them graded over the weekend. So, and get them back to you on Monday. Let's see, we have 2.5 weeks of class left after today. So really 2 weeks of lecture left. I think we've got another chapter and a half to cover in the remaining 2 weeks. So we want to get into, this chapter is still baseband digital. The last chapter we'll cover is actually modulated digital. So have a good weekend.